after teasing you in the last videos about what I failed and learned and that now goes into the next project, I want to show you my current project, which I believe will be a success, but you never know. But entrepreneurship is about trying stuff, right? It's that thing here. So basically, the idea is you can put a beer glass here. It gets moved forward onto a scale. From the top, I will fill it with beer. And after that, I move it out here. I even have an output slide, but not sure yet if that works. So basically, I just want to let it slide like this. And not against the cast iron block, but yeah. So basically, the idea is to automatically fill beer. One option is with the real German Maßkrug, because the idea came to me when I was at Oktoberfest. But for festivals and parties, I have this thing here that supposedly fits in here and eject one at a time onto the conveyor, and the conveyor moves it then to the scale, and then it gets filled. The filling module is now on the printer, so that will come soon, and so on. Today, I want to figure out how exactly my magazine works with the ejection of the cups. As actuators, I have beefy solenoids. The big issue with such solenoids is that they draw a lot of current. They have a high inductivity, so that leads to a peak of voltage when you turn them off. And that voltage peak has destroyed already many of my MOSFETs. I've got a bunch of MOSFETs I have fried. But these are AliExpress MOSFETs, so I'm not sure if they're up to spec. Which I bought here in Switzerland, so I'm pretty sure they are up to spec. And I have fast diodes that I need as freewheel diode. Now I will hook it all up and check, can I actuate my coils without frying the MOSFET. Fry a MOSFET, in most cases, it goes on always on. So it will just stay on. That's a symptom of a fried MOSFET. And yeah, I'm really curious to see if I can get it to run. So the basic principle is I have this little lever with this counterweight, and this counterweight pushes the lever towards the cup, right? The cup is held by this little notch here, and at the moment I start pushing down my lever, you see it will, through the geometry, push it past, and then it should fall down. That's basically the idea I have with my coil. I have two things to test now. One thing is the electronics to switch that big current, and the second one is the mechanics to eject a cup. So now, the moment of truth. Turn on the power supplies. I should have 24 volts and 3.3 now. And now, 3, 2, 1. And again. Yes! Mechanics don't work, but my MOSFET has survived. If I go 3.3, I go down, and if I go 0, I go up again. First success. I did not fry the MOSFET. And so, one learning from me, I don't buy MOSFETs on AliExpress anymore. No wonder how cheap they are. I mean, I can still use the cheap MOSFETs I got from AliExpress if I want to switch half an amp or so. But if I want to really switch beefy currents, I will get my MOSFETs from a local source, and this baby has done its job, and I'm very happy about that. So, having slow-mo footage of what exactly is happening when I try to shoot down a cup, that doesn't really work, and I'm really curious to know why it works on this side and it doesn't work on this side. But I have an idea, and that's why I'm gonna just try by experimentation. The idea I have is that at the moment I start shooting down here, I have I have this counterweight, which basically should push it in here, right? But with inertia, when I shoot that thing down, the counterweight will be pulled up since that point goes down, right? Because we have the inertia. And that's, I think, what's the issue. And so I think I'll have to redesign this whole thing to work with the spring instead of a counterweight, because then I don't have this inertia problem. So back to the drawing board, back to print, and I'll show you the next version if it works better or not. So these parts are finally finished. That was a 30-hour print. No! I broke my part. Shit. So let's see. That one. Oh. Tight but perfect. That's exactly the kind of fit I wanted. And now you see that little hole here? That's how I can then clamp it. And it will be, yeah. Maybe even too tight. No, it's perfect. No wiggling. Exactly what I wanted. And now comes the nice part here. Yeah, look at this. That's exactly what I wanted. Except that it's broken here. But it works even broken, so I can live with it. But I wanted to go around as tight as possible corner, but in the meantime not squeeze the hose. And that works. Okay. Validated. That's prototyping. You build something, you test it, and maybe you have to rebuild it, and maybe not. So now it's all together. This is what I call the pull pourer, because it pours liquid and it pulls in the meantime. Yeah, I have to assemble this part in the front here. It's not completely finished, but the idea is that I can move the hose down into the glass, and while I'm filling, I pull it. That's why I call it the pull pourer. And that is great for beer, because if I drop the beer from up here, I will just make foam. But if I fill it from the bottom, it will be much better. Also got a new spindle stepper motor. This one is from a German supplier. I mean, it's still a Chinese stepper motor. And I'm curious to see if it works better than this one, because this one is directly from AliExpress, and the only thing it does is noise. It doesn't want to rotate. Little bastard. Whatever. So I have to figure out if the other motor works better. You see, that one is thicker than that one, because and so I have a thinner spindle, so that means I need to change my part on the other side, but I have a 3D printer, and 3D printing makes it easy. Just quickly go into the design, reprint it, and it's a small part. But first I have to check if it runs. And then I also have to solder on that little button here to go into the front of the machine, to go actually into this hole here. And because then I can put in that one, because if I put that one in before having the button in, I cannot tighten the nut behind, and then everything becomes complicated. But then I can put this last part over there, and then the whole thing will be complete. So now that I know that the MOSFET is running, that the stepper drivers are running, that the sensors can be read, I have it all. I can do a proper PCB design. Let's hope I get it before Christmas. Then I can use it through the Christmas break. So let's go upstairs and do it on KiCad, do a little PCB design and order that little PCB. Okay, I found a solution for this guy, and I printed new parts, and I added a camera up here, see? And so, you can watch me better working. So I have these parts here, these parts here, these parts here, and I needed some way of pushing that little lever up. You remember the high-speed images I tried to make? I think that having that counterweight doesn't help me if I push down quickly, because then the counterweight through inertia starts pushing up instead of down. So I needed a spring. Now getting the right spring is usually not easy. So I found a hack and I'm curious if it works. I got this stuff. This is thickness gauge foil. So it has a calibrated thickness. This here is 0.1 millimeter. And it is actually a stainless spring steel. So you see it's very springy. And you get this in about all thicknesses you want. From 0.05 to about 1 millimeter. You get them in very different things for, I think it's 20 to 30 bucks for 5 meters of length. So you get pretty far with it. And you can do spring steel with that. That's the older design I had. So that's old. I have a very little slot going through here to put that leaf spring through. I am curious if it's still open after printing. I wanted to use 3mm rods everywhere. I couldn't find some 3mm rod quickly when I was looking for it. But these have exactly 3mm diameter. So I thought for a prototype they will also do the trick. So let's start with the leaf spring. I need 5mm width. Make it a bit narrower at the beginning so I can better put it in. Oh man, that was not a straight cut if I look at it now. This one, there we go. Number 1 is in. This one, and then number 2. Look how well this worked. So now, the moment of truth. Can I push it? You see that? So it should be able to push past this surface, because that's the rim of the glass. And then it should snap back to where it catches the rim of the glass. Yeah, it looks not too bad. And here we go. The brand new 2 cup pushers. The brand new 2 cup pushers are ready now. Now I want to test with the smallest glasses, so it goes all the way in. Cups in there. It might be even slightly too tight. So now I'd be curious to test it. But I know if I start testing it, I'll be testing it for an hour or 2. And it's already late. So I call it a day. And I'll continue tomorrow. I already had cleaned out my breadboard because I was thinking for a first version of a control board I will have to use the breadboard, because my PCBs I have designed last weekend actually, that they would not arrive before Christmas. Guess what I got? PCBs arrived. A handful of stepper drivers, the PCBs of course, 10K resistors, and some 10 micro capacitors. That's basically what I'm gonna need. No, 7. 12 here, 6. So 7 of these. 1, 2, 3, 4, 5 of these. this, that, so. Now comes the big moment. I have the whole board together, and now I have to hook it up to the machine. So we have the filling part, we have the conveyor part, and we have the cup magazine. It's all there. All wiring coming out here at the moment, because for the moment I want to have the board outside for debugging purposes. And so first thing I'm going to do is to hook up one sensor after another, check if I get signal on it, then do same with all the motors, and then we start with some higher logic like referencing and moving and stuff like that. But first, I need to check all wires if signal goes through and if my board doesn't start emitting smoke, which might happen. I never tested that board yet. I have my little power supply down here, set to 24.5 amps. Yeah, let's give it a bit more amps. 2 amps for now. Plus and minus are connected. I need 24 volts to activate my sensors. So, fuck! Now for all the other ones it's total blind testing because I don't know which wire goes where. I should have marked them, of course, but I didn't. Oh, that's this one. I found which one it is. It is... That's cup scale. Cup scale. I have to look here because I didn't put the proper silk screen on this. All sensors work. That's first achievement. And we have a changing number too. The scale is working. Now to the motor. So motor L direction. Motor L. That is motor L. So the conclusion is we have 2 working motor drivers where everything works. We have 2 motor drivers that don't send out a proper power signal to the motor, which I have to figure out. And I have 1 motor that I can connect to any driver and it still doesn't work. So for that motor, it's this one, it's the puller one. I'll need to recrimp the cable, and for the other 2 drivers I'll need to resolder all connections and check if that's the issue. So, finally, I could get my board up and running. All motors are finally working, which is a bit spooky because some of them I'm not 100% sure why they suddenly work. When you have bugs that disappear out of nothing, they have a tendency to reappear out of nothing. So fingers crossed that this will work. Now I had to, after writing just some snippets of code to test inputs and outputs, I had to really sit down and write a proper first version of the firmware to connect everything together and to also enable the web interface and the button, because then I can, with the web interface, send more detailed commands than originally. Originally, I just had variables in my code and was changing the variables, recompiling and running it. I mean, that's the quick and dirty way to just test something. But if you have done it a few times, you start wasting time on that. Then it's better to invest the time to have all these variables properly declared, having some way to externally control them so you don't have to recompile all the software. And so I also noticed many mechanical things I need to change. And so I printed quite a bunch of parts, even more than that, rethinking the mechanical design to fix some issues. which somehow worked and somehow not. You see how this here is distorted. The thing is, every 3D printed part, which is FDM printed, will contract when cooling down, and so it will have the tendency to lift off the print bed, which usually is not a problem if you have a heated print bed that leads to having less tensions in the bottom layers, and you have a good bed adhesion, so it's sticking flat on the bed. What I did on this one here is I had supports in between the parts. So I had support structures in here, and I printed it in this position. And so I had all this stuff here pulling on the support structure, and since the supports are very thin, since you want to save material, it led to this distortion. And actually in here I have a channel where this rod should be moving, and it just doesn't work. And I also noticed that the gear rack of the linear movement back and forth makes a hell of a noise. So that's an older version of that gear rack with the gears here. Well, on this side you see them. Now the thing is, a stepper motor, especially if I run it the primitive way like I do, full steps and the cheapest possible drivers, it will accelerate and stop, accelerate and stop, accelerate and stop. So that's why it's called a stepper motor, right? So what does that do with the gear? It does like that, right? It's always gonna push the gear and then stop again, and so it's always wiggling between the teeth. And since I have all the rest of the mechanism that also has play, everything like that. A lot of noise. So that made me think that maybe for this linear movement, a belt drive would be better. Belt drive like I have on my 3D printer, which is less noisy and also has other advantages, but that means a complete redesign of the whole machine. Or not the whole machine, but many parts. And also probably also redesigning the laser cut parts, which I have to order, which will cost me more money than just printing parts. That's the story of R&D. You have to keep iterating until it's good. For now, I will use the existing mechanics I have just to develop software and optimize the software. And also then in parallel do that redesign, order the parts, reprint parts to get the next mechanical version up and running. But for now, I think that's enough for this episode. Thanks a lot for watching. Check in the next episode where you see the existing setup, which is not perfect, but at least it does something, with the firmware together, where I check all the functions, how well they work. And then I can also show you what I'll be redesigning in CAD.